So if you see in the synthesis, for example, that the product has two OHs next to each other and their stereochemistry is the same, then most likely you had to do this reaction to get there. Next reaction is hydrogenation. We start with a double bond as always, and our reagent is H2 with the metal catalyst. The metal catalyst could be PD, PT, or Ni. What does it do? Well, we turn double bond into a single bond by adding two hydrogens, one on each carbon from the double bond. Hydrogens have to add syn. That means that they will be both on a wedge or both on a dash. So for example, I have my molecule here. This is my starting material. And I use H2PD. I'm going to turn double into single, and I'm going to add two hydrogens, one on each carbon from where the double bond was. And they will both be either dash here or wedge. So I would get, in this case, two products. Next reaction, ozonolysis with reductive workup. Notice we will have another ozonolysis. So we have two kinds of ozonolysis. Ozonolysis with reductive workup. First step, ozone, O3. Second step, CH3-2S. Or you can use DNH2O. CH3-2S is the most popular. Sometimes we call it DMS or sometimes Me2S, depending on how your teacher wants to write it. For the product, what we have to do here is we have to break the double bond in half, in two halves. And we have to add two oxygens, one on each end of the double bond broken. So here's my double bond. I break it in half, two halves, and I add an oxygen to each of the half that was broken. These are my two products. Notice if I have a double bond not in the ring, I'll have two products. But let's see what happens if I have a double bond inside the ring. Again, I break it in half, I draw it out, and I add an oxygen on each side of my two halves. Two oxygens get added. And guess what happens? We only have one molecule. So if I have one double bond inside the ring and I do ozonolysis, I'll end up with one product. But if I have it not inside the ring, I will get two products like here. Next, let's do ozonolysis with oxidative workup. So the first step is the same O3, but the second step has to be H2O2. That's the most popular step. There could be others depending on your professor, so pay attention, but this is the most popular second step for oxidative workup. And what we have to do is we have to break the double bond in two and add two oxygens, one on each end of the double bond broken. So same as we did before. But if we end up with an aldehyde, and an aldehyde is C double bond O in between a carbon and a hydrogen. So if we have a hydrogen, we have to change that hydrogen into OH to make carboxylic acid. So here we add oxygen to each half, but this carbon, it used to have a hydrogen. We will change the hydrogen into the OH group, and we will make a carboxylic acid here. Notice for this one, it was a ketone. It was not an aldehyde. This C double bond O was in between two carbons. So we can't do anything to it. We leave it alone. But it's this one that we had to change because this carbon had a hydrogen here. So we will have to change the hydrogen to the OH to make carboxylic acid. So if you see in your synthesis that you have carboxylic acid products, maybe that was ozonolysis with oxidative workup. You can think about that. Next reaction is called epoxidation. Epoxidation makes an epoxide. What is that? Well, let's start from the beginning. Again, I start with an alkene. My reagent is RCO3H. RCO3H is peroxy acid. Examples of RCO3H could be MCPBA, or for example CF3CO3H. MCPBA, I would say, is the most popular reagent used by professors. What we have to do is we have to turn double bond into a single bond, and we will attach the two carbons. that had a double bond to an oxygen, making an epoxide. So epoxide is actually looks like a triangle with an oxygen inside. And we also have to remember that when we draw the epoxide, here it doesn't matter, but the stereochemistry, the reaction is concerted. So when we make the epoxide, we will either put it on a wedge, like both of these would be on a wedge, or both of these would be on a dash. And later on, you will learn a lot of different reactions with an epoxide. So once you make this epoxide, you can react it further. Radical addition of HBr is the next reaction. We start with the double bond and we use HBr ROR. ROR is peroxide, so you use HBr peroxide. We have done alkene with HBr before. What's the difference? The difference is this second part, peroxide. That makes all the difference. And in this reaction, we turn double bond into a single bond and we attach bromine to the least substituted carbon from the double bond carbons. In the other reaction, without the peroxide, if it's just HBr, we add bromine to the most substituted carbon. But if we have the ROR, if it says peroxide, you have to add it to the least substituted carbon, anti-Markovnikov. So here we have a double bond, switch it to a single. This carbon is tertiary, this carbon is secondary. I don't know if it says secondary or not, but this is secondary. It's only attached to 2 carbons. So where do we put bromine? To the least substituted carbon. We're putting bromine here to the carbons that's attached to the least carbons. And let's go ahead and go over the last reaction, which is the Simmons Smith reaction. We start with an alkene and the reagent is CH2I2, zinc with CuCl. And here what we have to do is we have to turn double bond into single. So we turned it into single. And we will attach the 2 carbons from the double bond to another carbon, making a cyclopropane, basically a triangle. So in this reaction, we turn our double bond, we turn it into a single bond, and we attach the 2 carbons to another carbon to make a cyclopropane. And that's the product of the Simmons Smith reaction. This is Mayya Lucci. I really hope that you found this chemistry video helpful. Please like and subscribe if you like it, and I look forward to making more chemistry videos for you.